So we're going to talk about the powers of I and what I is and how we use it. You know, we're used to any other letter in the alphabet being used in algebra, like a 2x or a 2y or you know 3m. That when we see these letters, that it's considered an unknown number. There's a number that belongs there, but it's kind of a placeholder, like a blank. But with the letter I, it represents something different than just any of your other random letters that we use in algebra. It's actually representing the word imaginary. Kind of a strange thought. Imaginary numbers. Something from your imagination. You know, think of your imagination means something that's not real. It's imaginary. And what the letter I does is it helps us do some math that technically within the math system can't really be done. And let me show you what I mean. Okay, so the square root of 4, for example, it's basically saying what number was squared, what number times itself, two identical numbers times each other, that caused the number 4. And we would say, oh, it was 2 times 2. Identical numbers caused the number 4. And that's fine, that works within our real number system and everything, but when you have what we say is the square root of -4, we have a dilemma here because there are not two identical numbers that equal -4 when you multiply them. If they were both negative, it would produce a positive. If they are both positive, then they're going to produce positive again. There aren't identical numbers that are going to ever multiply to make a -4. And so we'd say, oh, wait a minute. If you were going to come up with an answer to this situation, if you had to come up with an answer, it would have to be an answer from your imagination, because there's no real answer to it. Nothing within our real number system, nothing within all the rules that we know about math and how numbers multiply, none of those rules work here. And so if we were going to represent something as an answer, it would have to be something from our imagination. And so that's where that word imaginary comes in, because we are going to find a solution to this, and it is going to include something that was imagined, a pretend kind of thing. And what they're going to do is they're going to say, okay, wait a minute. I cannot find the answer to the square root of -4. But if I broke this up a little bit into, workable parts, at least some of them, something I could deal with, I could call this 4 times -1 inside of here. And what that allows me to do is think of this as two separate pieces. I could say, okay, what's the square root of 4 and what's the square root of -1? And when I do that, I can complete the first part. I do know the square root of 4 is 2. So that part done, that fits within our real number system. I cannot complete this part. And so what I'm going to say is I'm going to take this answer 2 and I'm going to multiply it by an imaginary answer represented by the letter I. So the answer to the square root of -4 is 2 times an imaginary number. So every time we see an I, we should think, oh, that's the same as saying square root of -1. These two things mean exactly the same thing. So if I say, okay, if I have I squared, then that would be the same thing as saying the square root of -1 times the square root of -1. And when I have that, that actually gives me an answer of -1. I mean, think about it. If you have, let's say, the square root of 4 times the square root of 4, for example, okay, that would actually give me an answer of 4, because it would be 2 times 2. It actually ends up being what's inside the radical there. The square root of 25 times the square root of 25. Well, that would be 5 times 5, which would give me 25, which was what was inside this radical. So if we have the square root of -1 times the square root of -1, the answer is -1. So every time you have two sets of two i's being multiplied by each other, for every set of 2, you have an answer of -1. So if I have I to the 4th power, then I have two sets of I squared. And we already discovered I squared always equals -1. So if I have two sets of I squared here, like this, because I to the 4th is the same as I squared times I squared, then this is really saying -1 times -1. And so then that would be, so we would say, oh, I to the 4th, the answer is a +1, because -1 times -1 is +1. Let's try this. What if we have I to the 6th? How many sets of I squared do we have? We can make 3 sets of I squared out of the 6 i's that we have. And that means that's 3 sets of -1 being multiplied. And when you multiply these, you get -1 as the answer. So I to the 6th is -1. So kind of a shortcut to this is you can just take half of this exponent. So if I had I to the 10th, that gives me 5 sets of -1, basically saying -1 to the 5th power. Like up here we could have said, oh, this is 3 sets, so we could have said -1 to the 3rd power. Or up here, -1 to the 2nd power. Down here, -1 to the 5th power. And well, you have negatives, 5 negatives multiplied, that always gives you a negative. So that would give me just -1 as an answer. And you could write that out, -1 times -1 times -1 times -1 times -1. So let's say they give you a whopper of 1. Let's say they give you I to the 24th power. How many sets of I squared? And remember, I squared always equals -1. So I want to know how many sets of -1 do I have here? And I just take half of that number. So that means I have -1, 12 sets of the I squared. So -1 to the 12th power is a +1, an even number of negatives being multiplied. So I to the 24th is +1. I to the 110, let's say. Well, that gives me sets of -1, it'd be half of this number. That gives me 55 sets of -1. Well, an odd number of negatives being multiplied gives me a negative, so that's going to end up being -1. If I have 21, I to the 21. Well, cutting this in half doesn't really work. It gives me -1 to the 10th, and I have an extra I left over. I only used 20 of those i's. And so I would take -1 to the 10th, which is +1, times the leftover I. And so that gives just, positive I. If I have I to the 17th, well, how many sets of I squared would I have? which is the same as saying negative 1. So I would have 8 sets. That would use up 16 of these i's. And then I have a regular I left over. Well, 8 sets of negative 1 gives me a positive 1. And then I have I. If I have I to the 18th, or let's do 19th, I to the 19th. That gives me 9 sets of negative 1 with 1 left over. Well, negative 1 to the 9th power is negative 1. So negative I is the answer.